Schwarz inequality or sometimes called as the Cauchy-Schwarz inequality is a very important inequality, and as a first step towards understanding the inequality, we use familiar vector algebra, which we'll be more familiar with. So suppose we have two vectors A and B. We know that the dot product between these two vectors is given by the norm of A into the norm of B cosine of the angle between the two vectors. Now, since cos theta ranges from -1 to 1, we note that the magnitude of this will be less than or equal to the magnitude or the norm of A and the magnitude of B. That is obvious because cos theta ranges from -1 to 1. So when you take the magnitude of both sides, you can easily arrive at this inequality. And the equality holds good only when A is a scalar times B, that is A and B are parallel or anti-parallel. Now we can use the equivalence between dot product between vectors and the inner product between signals. So when we take that equivalence, if we have two signals, say S of t and H of t, if we have two signals like this, their dot product is the equivalent of an inner product, which is defined like this. This is the inner product. And I'll just write down the Schwarz inequality which I had here just now. In fact, it would be more appropriate if I write like this anyhow. And of course, I can also write like this because magnitude A square is nothing but A dot A and magnitude B square is B dot B. So when you translate this to the signals, this idea, the Schwarz inequality to signals, we see that since the dot product gets the equivalent of dot product is inner product, we have the left hand side to begin with like this, and then the magnitude square. So the dot product is here in the form of an inner product. The magnitude part we have taken here and we have squared it, and it will be less than or equal to magnitude of A square is nothing but a dot product between A and A, that is dot product of A with itself, and that gets transposed. So if you take this as vector A, the equivalent of vector A, we can write this as ST. It is an inner product of ST with itself, so ST into S conjugate T dt integral, which incidentally is the same as, since ST into S conjugate T gives us magnitude of ST square dt. And this part we have this part here now. This part would be an inner product of ht with itself, and that will give us into, so it's a multiplication here, ht, because an inner product of ht with itself would be ht into conjugate of ht, and an integral from minus to plus infinity dt. And remember, the signals st and ht are of finite energy, integrable of course. Now we will we will try to prove this inequality. There are many ways in which it can be proved, so I will just give a proof here in a slightly different way, and I will be making use of the idea of the series representation of finite energy signals. So what I am going to do is I am going to make use of the concept that st can be expressed as a series. I can start from sk1 to n sk phi kt, where sk are the coefficients of expansion and the phi kt's are the orthonormal basis functions. So the expansion of the idea of expanding a finite energy signal in the form of a series like this, right, expressing it in the form of a series using a set of orthonormal basis functions, is the method which I am going to use to arrive at this inequality. And similarly, of course, ht can be expressed like this. So this is the idea I'm going to use. With this, I'll try to prove this inequality. Now, we know that since we have only two signals with us, st and ht, since we have only two signals with us, we need to have at most two basis functions, because we will be operating on a two-dimensional space at most, because we have two signals with us, st and ht. It is like saying that if we have two vectors with us, we need only a two-dimensional space at most, and if those two vectors are actually linearly dependent, then you need only a one-dimensional space. So at most we need only two basis functions, say phi1t and phi2t. At most we need only two basis functions. We don't need more than two because we have only two signals. And the first basis function can be easily arrived at by dividing st with its energy under square root. So where Es is the energy of st, which I will define like this. So if when we do this, we get the first basis function, and you can see that the energy of this is 1. So it's normalized. And now we can get the second basis function. So this itself, this says that st is equal to root es phi 1t, which means that this is s1 and s2 is 0. Even before we find out what is phi 2t, we can say s2 is 0 because st has been completely characterized by this. So s2 is 0. Now we can find the other basis function, the second basis function, using the Gram-Schmidt orthogonalization procedure. So you must be familiar with that. So I'll just I will not go to the details of the steps. I will roughly explain what we'll be doing. What we do is, from ht we subtract its component along phi 1t to get this. So from ht I am subtracting its component along phi 1t. So when I multiply ht with this, this in fact gives me h1, and then this, if this as a whole gives me the component of h1t along phi 1, and when I subtract the component of ht along phi 1 t from ht, I will get a vector which is perpendicular to phi 1 t. It can be easily verified because if you multiply this with phi 1 conjugate t and integrate, you see the result is 0. Now we write this as ht minus, we call this as h1 phi 1 t. And to get phi 2 t, we have to normalize this because this is already perpendicular to phi 1 t. We have got the second basis function. If we just normalize this by dividing this with its own energy, we end up getting phi 2 t. So phi 2 t would be ht minus h1 phi 1 t divided by its energy. And the energy of this will be ht minus h1 phi 1 t multiplied by ht conjugate minus h1 conjugate phi 1 conjugate t dt. We can expand this. So I'll just show you a few steps. ht into ht conjugate will give h magnitude square t. So I will write down the final result because I don't want to spend time on this. The final result would be, after performing the integration, you will get the result as equal to EH, where EH is the energy of the signal ht, which is defined as an integral from minus to plus infinity of magnitude ht square dt, EH minus h1 magnitude square. So this is phi 2t. So we have the two basis functions now with us. Phi 1t is this and phi 2t is this. And we already know that st is expressed like this, can be simply written like this. It's nothing but the same thing rearranged, and we know this is s1. And from this we see that ht is equal to if we rearrange, ht is equal to h1 phi 1 t plus, so I take it over here and bring it here so that I get ht in terms of these. Ht is h1 phi 1 t plus square root of eh minus h1 square phi 2t. So I have the series representation for ht also, where this is h1, and h1 I told you already what is h1. h1 is an integral of ht multiplied by phi 1 conjugate t, and this would hence be h2. So h1 phi 1 t plus h2 phi 2 t, h2 is this, and we have the series representation of h2 here, ht here, and st is already been represented here like this. Now with this in our hands, with this representation in our hands, we write first the left hand side of the Schwarz inequality. So I take an inner product first, st into h conjugate t dt. This is the inner product, and I replace st with this and ht with this. So I get root es phi 1 t, that is st, and multiplied by h conjugate, so that will be h1 conjugate phi 1 conjugate t plus h2 conjugate phi 2 conjugate t dt. So this is what we do, and this is the left. I'm building the left hand side. I'm finding out the left hand side of the Schwarz inequality, and now this gives us root ES comes out. Phi 1 t into phi 1 conjugate t, if you integrate, so before that H1 conjugate also comes out, and phi 1 t into phi 1 conjugate integral will be 1, because phi 1 t is of unit energy. Phi 1 t into phi 1 conjugate t dt integral is nothing but its energy, it's 1. So the first term is this, and then we have this product, isn't it? This we have found out. Now we have this product, that would be plus root ES H2 conjugate into integral phi 1 t phi 2 conjugate t dt. Now this is 0 because phi 1 and phi 2 are orthogonal, they are orthonormal, they are the two basis functions, they are two functions from an orthonormal set. So this result is 0, which means that the left hand side, the inner product is this. So this is what the inner product between the two signals turn out to be. Now the square of the magnitude of this, which appears on the left hand side of this the Schwarz inequality, is this is what appears, this is what it has to be, which means you have ES, because this is real, H1 magnitude square. This is the left hand side. And what the inequality says is that, I will just write it here, it's a continuation. What the inequality says is that it's greater than or equal to, I'm sorry, this is less than or equal to S t square dt into H t square dt. So now clearly when you calculate this, you will see that energy of St is what you have here and energy of Ht is what you have here. Using the Parseval's, the generalized form of the Parseval's identity, this will be the same as S1 square plus S2 square. It can be shown easily that this is the same, because you just have, in fact, if you substitute for St as equal to S1 phi 1 t plus S2 phi 2 t, you will get this result, and S2 is 0, we already know, and this, as you know, is nothing but ES. So the first integral is nothing but ES into the second integral will be H1 square plus H2 square. And you can see that the inequality easily follows from this. So if I put it in other words, if I go the other way now, I can say easily that having obtained this on the left hand side of the Schwarz inequality, which I have shown you the steps through this, till here I came and then I said this is the result. If having obtained this, I can easily say that this will be less than or equal to this, because you have ES magnitude H1 square, you have ES magnitude H1 square plus H2 square here, so this will definitely be less than this, and the left hand side is this, the right hand side, as we saw just now, is this. So if I come till here, I can easily write that this is like this, and then I can show that this is nothing but this, which proves in a way the inequality. Now the equality will hold good. If you see this clearly, the equality is going to hold good only, and of course I can even say that this is EH, you know it's EH, because again from the generalized Parseval's identity, you know it is EH. H1 square plus H2 square, magnitude of H1 square plus magnitude H2 square is EH. So we can easily write this as EH. So ES into EH is greater than or equal to ES magnitude H1 square. That is clearly because I don't have H2 magnitude square here, which is getting added to this. So this is the proof, in a way, the proof of this is how we can demonstrate or prove the Schwarz inequality using the series representation of signals. Now, for the equality to hold good, because it's not complete unless we say what are the conditions to be satisfied, unless we demonstrate the condition which has to be satisfied if the equality has to hold good. Inequality we have proved. For the equality to hold good, we see that it is possible only if the entire energy of signal Ht is concentrated in this. That means H2 has to be 0. If H2 is 0, then the equality follows. So for the equality to hold good, the entire energy of the signal Ht has to be in H1 magnitude square. In other words, H2 magnitude square or H2 has to be 0. And that means if that has to happen, if the entire energy of the signal Ht has to be in magnitude H1 square, then Ht has to be a constant into phi 1t. If Ht is a constant into phi 1t, then the energy of Ht will be concentrated in its one and the only coefficient, which is getting multiplied by phi 1t, which means that this is the same as C S 1t by st by root es. That is C by root es st, which is nothing but the fact that ht is a constant into st. When that is satisfied, only then the equality holds good. Because when this is the case, as you know, ht becomes a constant divided by root es st, and st, as you know, is the same way. I put it again in a different way, is this, which means that ht is a constant times phi 1t. So this is the way we can prove the inequality first, and also demonstrate what is the condition to be satisfied by the two involved functions if the equality has to hold good.